record button, which means this session is now being recorded. So don't say anything you don't want to be recorded, I guess. And I am going to begin by sharing my application screen with you. I'm going to go to a PowerPoint slide, and let's see. Okay. Okay, so this is an outline of my talking points, and we do have some important content. So I'm going to call this to be, it's more about limits, and I expect to introduce a very special limit to you. Okay, and so we're going to be working till till we finish and so on and so forth. Okay, so that's what we have. So I'm just going to start talking. I am going to poll the group to see if you have anything that you want to raise. And by the way, for the most part, people have been raising administrative questions, which are fine. And I want to know about those, but also whenever we get face to face, I hope what we can do is I'm just going to come in. I'm not going to poll everybody, but what I am going to do is I am going to come into the classroom and say, okay, are there any questions? And we'll start the period with questions. So I hope you're conditioned enough and comfortable enough that you say, yeah, I can raise my hand and ask questions there. Okay, now this should be the last day that we're meeting remotely like this, and I'm very hopeful that that's the case. And on Monday, at least at this instance, I plan on going into the classroom. Now, I heard wind last night of a rumor, and it's probably a true rumor, that they're extending the deadlines for student compliance, but that has nothing to do with what you do other than that you go to, you come to the classroom on that day. And I think things will work the way I suggested that they will. Now, I do have a couple of videos that are going to be rendering. And I will be saying, hey, watch these. And these deal with consideration of infinity and the number e. Now, what I'm going to do is I'm going to talk a little bit about those in the content today, of more about limits and a special limit. But I'm going to be focusing on the special limit. And let me maybe change this. Let's see, is it easy to change this slide? Maybe it is, maybe it's not. We'll see. Okay, but I'm going to be focusing on the special limit, although we'll spend some time doing that. And then your questions and answers are always welcome. So anyway, that's what's in store for us today. And I think I will move directly to the polling. So I'm going to stop sharing this, and I am going back to Blackboard, and I'm going to look at these students who have joined us this morning. And here I have a handful of students, so that's good. And I'm just going to go through and call on you one by one, just ask if you got anything you want to share with the class or any issues. And again, I am concerned about you. I do want you to, I'm going to be asking, and I'm going to start with Alex, I guess, today. So Alex, how are you and yours? And do you have any questions or issues you want to raise with me and your classmates at this time? and sometimes there's a bit of a delay as people, try to figure out, well, do I go on mic or do I type a comment or what? And sometimes people are going and letting their dogs outside and things like that. So, Alex, are you with us and are you doing okay? And do you have any questions?
Yeah, sorry about the delay on the audio. I am all good.
Okay, great. And again, don't I actually told a student yesterday that taking math at the college as a PhD means never having to say you're sorry, and that's like a quote from an old movie that we won't talk about. But anyway, okay. And actually, the movie was not about math. In fact, the actual quote from the movie was, "Love means never having to say you're sorry." Anyway, let's go to Artemio, and anything on your mind this morning, and how are you and yours?
Thank you. My morning is good, but I don't have any questions.
Okay, so we will move on. Cecilia, you are next in alphabetical order. And so do you have anything you want to raise with the class or me at this
No,
time?
no, we've already discussed what we need to discuss.
Okay, so we're in good shape then, at
So
least for
far,
now.
yes. I'll let you know if I have any more questions, though, if I
Well,
end up getting them.
okay, and certainly please feel free to do that. That is good. Thank you.
No
Okay,
problem.
Herr Patel, how about you?
I'm good. I don't have any questions right now.
Okay, excellent. Jeffrey Weinholz is next. Jeffrey, how are you and yours? And do you have anything worth, I don't mean worth sharing, and anything you want to say is worth sharing, but do you have anything you want to share with us at this time?
I'm doing good, thank you. And I'm all good. I don't have anything to talk about at the moment.
Okay, well, if you do, just shout out, and we'll deal with whatever questions might be there. Joseph Vaselli. Joseph, how are you today? And is there anything you want to share with me or the class?
I'm doing good. I don't have any questions either.
Okay, excellent. It would be excellent if you had questions too. That's all fine. Mark, please, Zayden.
I'm doing good, and I have no questions.
Okay. And I have Michael Showman, it looks like. Michael, how are you and yours? And do you have anything you want to ask or raise at this time?
I'm doing good, and I have no questions.
All right, excellent. That's good. We'll move on to Timur. Timur, same questions to you, please. Anything you want to share with the class?
No, I'm fine. Thank you.
All right, excellent. And okay, so we will continue going on. And let's see, last but not least, Tony Beliza.
Hi, I'm doing well. Thanks for asking, and I don't have any questions.
All right, that's good. So we did polling, and again, your questions are always welcome. That's why I'm here, is to teach math, and part of that is answering questions. Okay, so now I'm going to share again. Let's see, do I want to share? Yeah, I am going to share an applications screen with you. And it's going to be a PowerPoint thing, and I'm just going to go down, and we're going to do some problems. But actually, I was sharing that. I think what I want to do is share a whiteboard with you. Okay, and so I did not share the right thing with you, so bear with me. And I will share a whiteboard. And so, all right, so so you should be seeing a whiteboard now. Okay, and I'm going to be typing something, and again, the way this technology works, I have to be finishing typing before you can see it. But previously, we considered, and let's just look at what we considered previously. We considered this, the limit as x tends to c of f of x equals L. But we were constrained that C was a real number, and likewise L was a real number. Okay, and I was typing that, but now you can see it. Okay, so today what we're going to do is we're actually going to relax both of those things. And what I mean is, and by the way, when I say today, these are the videos that are being rendered and that I'll make available for you, where I talk about these in a lecture sense, and I give you definitions and do you know, a bunch of examples and things like that. But I don't want to ignore talking about it in class in case there's questions. So what we're going to do is today we will talk about what it means for L to be plus or minus infinity, and what it means for C to be plus or minus infinity. And I'm going to, in keeping with the way I'm trying to do things, I'll write that down too. Today, we consider first the case where L can be plus or minus infinity. And after that, what it means for C to be plus or minus. Okay, so that's what we're going to be about. Okay, and maybe just to be complete here, I'm going to capture this as a snip, and I'll make a slide that looks like this. Okay, so we got that, and I'll go back to the PowerPoint slide, and I'll make a slide there. Okay, so that's what the first part of this of today's discussion is about. Although I'm making a video about this, so this is just really going to be working a couple of problems. All right, so let's look at a couple of problems. Again, you should be seeing the PowerPoint slide, and this doesn't say I'm sharing the screen, so I
Yeah, you are
probably
not
screwed
sharing.
that up. Yeah, let me go fix that. Okay. All right, so I need to share an application screen, and we'll do that and this. And thank you, Ms. Patel. That was excellent that you helped out with that. That was good. Thank you. And I'm going back, and soon we will see it. And now I can also see that I am sharing, so this is good. All right, and I've got some problems here, and I am going to work these problems pretty much on the whiteboard. And I'm going to look at three of these. I'm going to look at, so the first one I'm going to do is 7, that is f of x equal 1 over x minus 4. And I'm going to turn that into a limit problem and just, you know, talk about that. And then I'm going to look at, for my next example, I'm going to look at 1 over x minus 4 whole squared. And last but not least, I am going to look at 10, which is minus 1 over x minus 4 whole squared. Okay, so I made some notes about this, and now I'm going to go to a whiteboard, and we're going to talk about what happens here. So I have to stop sharing here, and I have to go back and I have to share differently, and so I'm going to be sharing a whiteboard. And I'm really going to, since I made a copy of this, I can erase all of this. And so all of this is now erased. Okay, so now I'm going to be talking about a real problem. Okay, so here's what we're going to do then. We're going to say, what is the limit as x tends to 4 of, and the function that we're studying is this one. This is 1 over, this is x minus 4. Now you might recall that we talked about, doing things analytically, we talked about things doing graphically, we talked about doing things numerically, and in the video I go through a whole bunch of that stuff. But I'm just really going to draw a little bit of a picture here. And what I'm going to do is, my picture will not be great, but you can use your imagination a little bit. Let's just think graphically about this for right now. So that is what I got with that line. Then I'm going to do another line here like this. These are going to be the X and Y axes. And I could draw those pretty well. The rest of this is not going to be nearly so good. Actually, there's one other thing I can use a line for, and that's right here. And this is going to be it's the line again. And so this point right here is going to be the point 4. And maybe I can do one more thing like here. So this is the point 4. And I'm going to be talking about the graph of this. So we have that going on. And this point is 4. That didn't line up well, but that's kind of okay. Now what happens, and I don't know if there's a good way for me to do dotted lines here, so I'm not going to worry about trying to do that. This will probably be, kind of sloppy, but I think you'll understand the idea. I'm drawing a vertical line and I'm drawing it dotted. So the dotted line that I'm drawing is the line that is that would be described as x equal 4. So that's where x equal 4. And if I substitute 0 in here, I get minus 1/4, which means this thing intersects just below the axis there. Okay, at 4. And if we graph this, what will happen is we will get the following graph. And I need to use my pencil now. And this will be kind of a sloppy graph. Let's see what. So I'm trying to, I guess I need to get a color. And I guess I will drew this in, I don't know, kind of a reddish thing. I'm not sure. But that's the graph that you would get with that. And of course, this just keeps going on and on and on. And then likewise, I would get this graph here. And that just goes on and on and on. Now, what you see is that when I approach the point x equal 4 from the right, it increases without bound. It just gets bigger and bigger and bigger. And if I approach 4 from the left, this gets this decreases without bound. And so we get this. So you see the limit from the left and the limit from the right are not the same at all. That means this is discontinuous. We call this a vertical asymptote. And the answer here is the limit does not exist. And we knew that limits, it was possible for limits not to exist. And so, we sort of knew that could happen. Now, this is nothing new because we would have said this limit, didn't exist before. but I wanted to get you used to thinking about vertical asymptotes and things like that. And I do a lot of definitions and all that kind of jazz in the video that I'm preparing for you to watch, but I just wanted to get here. So I'm going to count to 10 Mississippi in case anybody wants to talk about this example. Then I have two more of these kind of examples I want to talk about. Okay, no one's raising any questions, so maybe you feel good about that. Before we leave this, though, I'm going to note that there's something else that's going on. We have a horizontal asymptote, and that means as the absolute value of x gets large, the function approaches 0. It never gets there, but we're talking about limits, so it approaches 0 as x goes to infinity, and if I'm going to positive infinity, it approaches 0 from above, and if I'm going to negative infinity, it approaches 0 from below. Okay, so that is good, and I think no one asked any questions, and no one did. I'm going to go to my next example, which means I'm erasing all of those things. Okay, and since I'm making a video, I'm not going to worry about going back and cutting that and making that into a slide. You could see it if you watch this video again. Okay, and again, it is a little bit tedious, but I'm going to need my graph again to look at this next one, so bear with me while I create yet another graph. Now my next example is going to be different, and it's this one. And this one is the limit. Again, I'm going to say x tends to 4. But now this time, my function is different, and I'm going to do 1 over, and this is x minus 4 whole squared. Okay, now again, this is going to hit, actually that's a lie. Can I undo that? Not easily, but that's kind of okay. So I'm going to graph this, and here is 4 again, and here is my vertical asymptote. But now the graph of this looks different because this one goes like this. And this is where I screwed up, but and it goes like this. Okay, now when you look at this, what you see is, oh, as I approach 4 from either direction, it grows without bound. And so what we're going to say in the video and say is that this limit is plus infinity. Now, I understand why in your textbook they say, well, the limit doesn't exist as a real number because infinity isn't a real number. But the answer to this question, what is the limit as x tends to 4 of 1 over x minus 4 whole squared in the denominator? The answer to this in this class is plus infinity. And it's kind of a difference in semantics. And it's kind of like if I showed you a picture of an Oreo cookie, some students might say, oh, that is an Oreo, and other people might say, oh, that's a cookie. And no one would be right or wrong. It's just people are calling it differently. So this is an example of something going to plus infinity. Now notice that we have expanded our universe now to allow the L that I was talking about earlier to actually be plus infinity. Now similarly, and the last example that I have is this one, where I just look at this. Now the answer to this one is different. And let's see, I need to get an eraser here.
Are you? Oh,
I'm sorry.
oh, I thought you were sharing PowerPoint.
We're okay, right?
Yeah, we're good.
Okay, excellent. Now I've changed things here, and this is not going to be true anymore. But I'm going to draw a graph of this just to show you what happens. Now here, by simply putting that in, here is what I get. There's like a thing there, and I guess I should have been using red there, and I got lost in. I'll try to do red again. I don't know. Red, and then we'll go to the pencil, not the eraser. And okay, so this one, if you think about the graph, and again, I do a lot more of this in the video that I'm going to be rendering and sharing with you, but I just wanted people to be comfortable with this. Is this what happens as I approach 4 from either direction is the same. It decreases without bound. And so the answer to this problem would be the limit as x tends to 4 of -1 over x minus 4 whole squared is minus infinity. And from this point on, and when you watch the videos, we're going to allow plus and minus infinity as being answers. But also, it's possible with vertical asymptotes to have the limit not existing like the first example that I did. So I'm going to pause for a count of 5 Mississippi here, just in case people have questions or comments they want to raise on this. Okay, I didn't hear anything, so I'm going to say that that's probably good for this. Now I'm going to go back and I'm going to pick up some other problems to share with you. So I will be sharing the application screen again, just to grab some problems that I have put down. Now this one is done, but now we're going to this next one. Now these are quite different, okay? And so what I'm going to do with this one is I'm going to write a few of these examples down. And I'm going to say, okay, so I have that one. I'm going to do that one. You'll see the ones I'm doing. Okay, so I've got that one. I am going to do that. Maybe I'll do 4 examples here. I don't know if this is, it'll be fine. And last but not least, I'm doing this one. Okay, that is good. Okay, so now what I'm going to do is I'm going to stop sharing this, and I'm going to go to Blackboard and share I'm going to share a whiteboard with you. And there it is. I'm going to erase this whiteboard because we don't need that anymore. Okay, so now what I'm going to do is I'm going to write the problem that we're going to be considering. And this is the limit Okay, so this is going to be the limit as x tends to plus infinity. And again, you don't always have to write the plus infinity, but I'm doing it here with this one. And this is going to be x over And this is going to be x squared plus 2. And I'm going to sketch a picture of this for us. And again, I do more than talk about the picture of these kind of problems in the lecture that I'm rendering right now and will be posted on YouTube later for you. And I will, I would encourage you to go and, watch that. Okay, and now I'm just going to sketch a picture of this, and the picture will be, I have to do the drawing, and I'll do it maybe in a different color just for the heck of it. I will call it red. Now, it turns out that this is equal to 0 here, but it will do this, but then it will drop down after a while, and we'll get that. And then it will continue here. It is what we would call an odd function. That should be completely symmetric. It might not be, I mean, certainly it's not because I just sketched it, but we get that. But okay, so what is the limit as x tends to plus infinity? Well, if you look at the picture, we're getting closer and closer to 0 as this gets closer and closer to infinity. And so I will say that this is equal to 0. And I think that's true very clearly from a graphical point of view. And now I'm going to say something. I'm writing it down. And you won't be able to see it until I'm finished writing it, but you will see it. This limit was 0 because the degree of the numerator was larger than the degree of the denominator. Okay, so there's actually a good takeaway there, okay? And what that says is that the limit, well, okay, I guess, so if you have a rational function, that means a quotient of polynomials, what will happen is that if the degree of the numerator is less than the degree of the denominator, it's going to go to 0 because the denominator, as x gets bigger and bigger, it will tend to wash that out. So that's what we have. That's kind of the, I guess, big takeaway here. I am going to say note. Let's see. So I will say note. And we're noting something here. Hold on. Okay, so I guess I'm good there. I'm still going to be red. Note, and I'm going to write this, the limit as x tends to minus infinity of x over x squared plus 2 was also equal to 0. That's not always true, but it's true here. Okay, so those are the things. I'm going to pause for a count of, I don't know what it is, 10 Mississippi, maybe, in case people want to ask questions about that. The big takeaway were the words that I put in the middle. Okay, that's good. Okay, so I'm going to erase this then, since there were no questions, but we did discuss that's something kind of important. Okay, Now we're going to erase that, and I'm going to write a different problem here. And I'm going to write this one as an example. And so this is the limit as x tends to infinity. And now this time, since it's not negative infinity, I just wrote infinity. That means it's positive infinity. And the function is this one. This is 4 sine x all over x squared plus 1. Now you know that sine oscillates. It goes from plus to minus 1 as you go along the real number line. And so there's a wiggle in this. But what I'm going to do is I'm going to sketch this. And we'll look at what's happening. So that's going to be a y-axis, and I'll get an x-axis too. Okay, so you see this top thing is oscillating back and forth between plus and minus 1, but the bottom is x squared. But the important thing to remember is that the top is bounded. So I'm going to sketch this, and again, it's not going to be a perfect sketch. It's just going to be a conceptual sketch. And red is fine for my color. So I'm going to talk about what happens here. Okay, so, and by the way, if I put x to be 0, I get 0, but here's what I will get. Okay, so you see this function as x goes to infinity is, sometimes it's positive and sometimes it's negative, and you got wiggling going on, but the top is bounded by plus or minus 4, and x squared in the denominator is going to get ginormous, and so the answer to this problem is 0. Now, sometimes it's up and sometimes it's down, but the answer to this problem is 0. So the limit of this is again equal to 0. Now, notice that it's equal to 0, but it's not an asymptote because sometimes it's above it and sometimes it's below it, and it just keeps wiggling. But the wiggling is damped out. Okay, so I'm going to write maybe a takeaway here for anybody who's trying to catch takeaways. The fact that the numerator was bounded leads us to the conclusion that this limit is 0. Now you can see what I was typing. Okay, I'm going to count for, I don't know, 10 Mississippis in case people want to do this, but realize that this is a fundamentally different question than I was asking before, because we're letting the limit on x going to 0, that the infinity is not where it was before. So we talked about a couple of examples. Are we okay with this? Okay, I didn't hear any questions, which must mean you're good. And by the way, I really do, and especially when we're in the classroom, if there's something going on that you want to ask about, please ask about it. You're doing yourself a favor because you're raising a question that you have immediately. You're doing your classmates a favor because some of them might really be having the same question, but they're too timid, or I mean, whatever. They aren't asking the question, but you help them, and you're actually helping me because who knows, I might have misexplained something, or I can explain something in a better way. Okay, so your questions are again always encouraged. Okay, so I'm going to erase this guy, and we're going to talk about yet another example. So this time we're going to talk about, I need to get a pencil again. So this time the example we're going to look at is the limit as x tends to infinity again. And that's, I didn't draw that well. That looks like a pair of glasses, but that's infinity. And this time I have this. 2x squared minus 3x plus 5 over. My denominator this time is x squared plus 1. Now this time, what's going to happen is, first of all, the denominator is never going to be 0, because if you square a real number, you get something that's not 0, and I'm adding it 1. So, you know, this is what's called a rational function. But the big difference between this one and a rational function that we talked about earlier is that the degree of the numerator, the polynomial in the numerator, is the same as the degree of the polynomial in the denominator. So that's what we've got going on here. And that makes all the difference in the world. It's a different theorem. Okay. And I'm going to do something a little different over here before I draw a graph of this. And so, in fact, maybe I'm going to do something completely different when I draw the graph of this. But okay, so I'm going to get that this is the limit. I'm doing something algebraic now, or analytic. X goes to infinity. But now you see, you never really get to infinity because this is still the same concept of the limit. You never really get there. You just say, what happens as I get closer and closer to it. And so what I'm going to do is, since it's not infinity, it is still a real number, I'm just going to take a value of x and I'm going to divide the top and the bottom by x squared. Now, when I do that, I'm dividing the top by x squared. So when I divide 2x squared by x squared, I just get 2 minus, and then I'm dividing by x squared. So this is 3x divided by x squared. When you do the calculation, it is 3 over x. And when I divide 5 by x squared, get 5 over x squared. Now, I'm not changing the value of the limit, so whatever I did to the numerator, I have to divide by the divide into the denominator. So I'm dividing x squared here by x squared. I get 1, and this is plus, and this is 1 over, and this is going to be x squared. But now we can use prior art, because we know that the limit of the quotient is the quotient of the limit if it exists. The limit of the sum is the sum of the limits if they all exist, and so on and so forth. So I'm going to look at what happens here as x goes to infinity. And I'm going to declare that this thing goes to 0. Because the denominator is of degree 1, the numerator is of degree 0. Similarly, this one goes to 0 as x gets big. And what that means is that the degree of the numerator is 0, the degree of the denominator is 2. So by that first discussion, the first example, we know that that goes to 0. And down here, this one goes to 0 as well for similar reasons. So as x goes to infinity, this whole thing gets closer and closer to 2. So the answer to this one is going to be 2, because whenever the, in fact, I guess I'll write that down somewhere. Okay, so I'll write it up here. The takeaway. Whenever the degree of the numerator equals the degree of the denominator. I can't spell this morning. The limit is the ratio of leading coefficients. Comma, and we observe a horizontal asymptote. And now I will flash off that, and now you can see what it was typing. Okay, so this is an important takeaway, and I am going to show you graphically what's going on here, but rather than try to sketch a woefully inadequate graph here, what I'm going to do is I'm going to leap onto Desmos and just show you a good picture of this in just a moment. And so you can see that, but you'll observe that, yeah, 2/3 is what you learned in your pre-calc was a horizontal asymptote. Okay, so now I know I haven't drawn the picture yet. I'm going to draw a picture, but do we have questions yet, or are we okay? I'm going to count to 10 Mississippi. Okay, no one asked any questions. And so what I'm going to do is I'm going to be leaving this, and I'm going to share my application screen because what I want to do is draw you a picture of this. I'm going to open a new browser window, and I'm going to go to Desmos. And we'll just go to Desmos, and let's learn together. That sounds good. Okay, so we're at Desmos, and I'm just going to graph that. Y equals, now my numerator, and I got to put this in parentheses if I'm typing it here. So this is 2x squared minus 3x plus 5. And then I'm going to put my parentheses there, of course. And I have to divide that. I need a parentheses in the denominator too, because Desmos will do exactly what I ask it to do. And if I screw up, she will do that. Okay, so there's the picture. And I am going to graph another thing here just so you can see what's going on. And so here I'm going to graph, let's see, how do I want to call it? I'm going to call it y equal 2. And that'll show up as a different color. Okay, so y equal 2 shows up blue, and I'll, let's see, do I want to go in or out? I want to go out. Okay, so what you can really see with this picture, I hope anyway, is that now, and by the way, I guess certainly that is a horizontal asymptote, but this is one of those weird situations where the function actually crosses this horizontal asymptote. And you can see that it looks like it crosses at x equal 1. I didn't check that, but that's probably true. Okay, so anyway, you see it like that. And so we can see out here that the limit as x goes to infinity is 2/3. And also the limit as x goes to minus infinity is also 2/3. Okay, so I'm going to pause here for a count of 10 Mississippi in case anyone wants to ask any questions about this example. And we only are going to look at one more of these things. Okay, so I'm going to stop sharing with you, and I'm going to go back to the, let's see, back here, and I'm going to share the whiteboard with you again, and I'm going to erase all this stuff because we're going to do one more example of these kind of things. And so this time we're going to take the limit, and I'm going to take this to be the limit as x tends to, I'm going to do plus infinity here. And I'm going to have 2x in the numerator. This is one of those problems I showed you before. And the denominator, I have the square root of, and this is x squared plus 2. Now I'm going to do a graph of this in a moment. I'm just going to use Desmos so you can see what happens. But here's algebraically what I'm going to do. Let's see, I guess I need to, I will say note, I guess. And now I can't, it's like an equation or something. But I'm going to remind you of something that I'm sure your algebra teacher taught you, but you might not remember. But this is important, and actually this is important in Calc 2 also. I end up talking a lot with students about this in the Learning Commons. The square root of x squared is not x. It's the absolute value of x. And let me demonstrate that to you with an example, okay? And so the example I'm going to say is, suppose I wanted to talk about the square root of, I really didn't need that parentheses there. Okay, so suppose I wanted to talk about the square root. I need to go get my pencil again. The square root of, and I'm going to use a number here. And so you see this is -6. So this is the square root of -6 whole squared. Well, the square root of -6 whole squared, first thing you do, order of operations, is you go inside the radical and you square that. So this is the same thing as the principal square root of 36. And whenever I use this symbol, the principal square root means it's always bigger than or equal to 0. That's the reason whenever you quote the quadratic formula, you will say plus or minus 6. Plus or minus the square root of b squared minus 4ac, excuse me. So anyway, the principal square root of 36 is just 6. Well, look, x in this case was -6 because that's what I was squaring, but the answer to the problem is 6, which is the absolute value of -6. So you see, that means there's some stuff going on here. And I'm going to just write an algebra thing. That's one algebra thing. And now up here, I'm going to write some more things. So again, this is limit. And this is going to be x. And I don't have a lot of space here, and I don't write very well on a Collaborate Ultra whiteboard and so on and so forth. So I'm probably going to skip a step, but that's kind of okay. Maybe I don't want to skip that step. I don't know. I'll do this. All right. So I'm going to factor x squared out of there. And that is going to be 1 plus, and then this is 2 over x squared. Okay, so that is certainly true because I'm just doing algebra. And now what I'm going to do is I'm going to say that this is the same thing as 2x over, and this is I'm using properties of algebra, I guess. So this is, and this is going to be x minus, not minus, it's infinity. But now I have 2x over, but the square root of the product of the radicals is the same thing as the square root of x squared, which I told you the square root of x squared over here was x, or absolute value of x. So that's the absolute value of x times the square root of 1 plus 2 over x squared. Okay, now as x goes to infinity, then x is becoming positive eventually. So I got x and positive x, those are going to cancel. And so in the numerator, I'm going to get, I can cancel this absolute value x with that because they're positive, and I get 2. And I can just plug in infinity in the, I'm not plugging in infinity, taking the limit, but these are continuous functions, so I can split the limit inside the continuity. And this thing, this part goes to 0. So this becomes 1. Now I'm going to pause for a count of 5 Mississippi in case anybody wants to talk about this. Okay, I hit 5 Mississippi, but now what I'm going to do is I'm going to change the problem just a little. And I'm going to make this minus infinity. So what changes? Well, this changes to minus infinity, of course. And I get a minus infinity there. And that's all good. But something really important happens here. You see, when we're going to minus infinity, x is going through negative numbers, isn't it? And so x, and the absolute value of x is always positive. The answer to this problem is minus 2. So I'm going to pause for a count of 5 Mississippi in case anybody wants to ask questions about that. And if not, we'll move on to something else. Herr Patel, are you guys still hearing me?
Yes, we can hear you.
Okay, excellent. And by the way, the reason I ask is I might be sitting here saying, boy, I'm giving a brilliant lecture, and if nobody's hearing it, it's kind of like if a tree falls in a forest and no one's there to hear it. That's actually a physics question, but you know, it's only good if people are hearing it. So thank you for responding to me. You've confirmed that people are out there. Okay, so that is good. Okay, and we'll get rid of that. And we're going to go back to, I am going to share my application screen with you. And we'll look at a PowerPoint slide again. And I'm thinking about things as we're going along, and I am changing my mind a little bit. This is in the video, so watch it there. Okay, and I'm just deciding that the best way to proceed right now is to move on to what I really hoped was going to be the fundamental topic. Okay, so now, I'm just changing in real time because I'm always watching the clock for you, and I want this to be the very best day that you've got. And I guess to do this, this is only in the video I plan to post later. It's rendering right now. Okay, so that's something to really look forward to there, and that's important. I already did the polling, so we're down here. Okay, now this thing down here is I want to talk about a special limit, and the special limit is called. And by the way, you might be saying, oh, we're finished with limits. No, calculus is the study of limits, and we're going to be talking about limits the whole term. But we're ready to talk about a very special limit that I'm going to introduce you to today. We'll see how far we get. and I'm trying to type it in here. Let's see. And this spatial limit today is called the derivative. Okay, so we're going to be introducing the derivative today. And I know I didn't tell you I was going to do cockpit commentary, but if I get to defining the derivative with you today, I think we've had a great 2 weeks. Okay, and we're 2 weeks into a 16-week term, but reaching the derivative today is good. Okay, so now I'm going to stop sharing this, and I'm going to share with you. Now we're still in the applications. No, I stopped sharing. I have to go back and share again. Hold on. Okay, so I'm sharing again. I'm sharing my application screen again. So I'm sharing. That's all good. But you're not seeing what I want you to see yet, but you will soon. And I'm just going to go here and bear with me because I need to find where I want to be. Okay, all right. So I'm lecturing a bit, and you should be looking at some notes from a textbook. Okay, there's a whole bunch of applications to this, but what I'm going to do and what I'm really talking about right now is the tangent line problem. So it says calculus grew out of 4 major problems in the 17th century, and number 1 is the tangent line problem. That's what we're going to talk about, just the tangent line problem today, but that is important. Okay, now let's look at this picture that is figure 2.1, and Herr Patel, we're still together?
Yes.
Excellent. Okay, so we're looking at a picture, and this is a tangent line to the circle. And one of the things that you learned along the way, back in your geometry days, was that the tangent line to a circle is perpendicular to the radius drawn to that point. So the tangent line at a point P is perpendicular to the radius of the circle drawn to that point P, and this is kind of reflecting that. And yeah, that's a tangent line, and back in the day, you probably did constructions when you studied high school geometry, and you did constructions of this. That's what I teach, my geometry students when I have geometry students. So that is a tangent line, and that's kind of clear. It's not quite as clear. Oh, maybe what is the tangent line here? Because in the first part, well, I guess it's pretty clear. If I have this y equals f of x that looks like a downward opening parabola, and I have a point P, which ostensibly is the vertex, we can see that, yeah, that horizontal line is clearly the tangent line. But in both the circle case and this case, it only touches the curve at one point. You might say, oh, well, that should be the definition of a tangent line. Well, it kind of can't be, though, because look at this middle picture, and you see that I'm drawing a tangent line to the point P, but it crosses the curve other places. And in fact, you're seeing the same thing happening on this middle picture and the other picture. So you see, it's a little bit complicated. What would you define to be a tangent line at a point? So we are going to talk about what is that definition going to be. But if it's a line, we know it looks like y equals mx plus b. And if we have a point, the only thing we need to know is the slope. So what we're going to be doing is we're going to be focusing right now on finding the slope of the tangent line. And I think this is way at the end of the lecture, but I'm going to do it now anyway. There was a great thinker who was Rene Descartes. You've maybe studied him in your philosophy classes and things like that. He is the guy who said, "Cognito ergo sum." That's Latin for "I think, therefore I am." He was a great philosopher, a great scientist. He was a French dude. Anyway, this is what he said about the tangent line problem, the problem that we're talking about right now. And he was a great deep thinker. And you might say, well, yeah, but this is a freshman calculus course. Well, we've come a long way since then. But anyway, Rene Descartes said, and I dare say that this is not only the most useful and general problem in geometry that I know, but it's even the most useful and general problem that I ever desire to know. So this really, intellectually, this was a really big deal. Okay, so let's go back then and start talking about this. So the question that we're thinking about is, how would we find the slope of the tangent line to a curve at a point? Well, what we're going to do is we're going to consider a secant line. So we're going to say, well, what we really want is the tangent line to the curve at this point C, comma f of c, but we're going to look at something that is called the secant line. And by the way, secant here does not mean the trig function secant. Secant is I think originally a Greek word, and it means to cut. So you see what you're doing here is you're drawing a line that does go through the point C, f of c, but you're picking a nearby point, which is near C. In fact, this point is C plus delta C. So we go over delta this way, and we're at the point C plus delta C. And by the way, if you and you can see this point is on the curve, so the y coordinate of that is, if the x coordinate is C plus delta C, delta x, the y coordinate is going to be C plus delta x. So we're going to say, well, what's the slope of this line? And we studied that before. So this one up here is y2 minus y1. This is, excuse me, this point up here is x2 and y2. And this point down here is x1, y1. So you see the slope is going to be the change in y over the change in x, or it's going to be f of c plus delta x minus f of c all over delta x, which is, so using this point up here and this point down here, I can compute the slope of this secant line, which is blue. Now, you might say, well, yeah, but that's just the secant line. That's not what I want. But what we're going to do is we're going to say, well, we're going to let delta x get smaller and smaller. So that's what this figure is doing. So here you see delta x being here, and then delta x gets smaller and smaller and smaller, and you can see the limit geometrically as delta x gets smaller and smaller and smaller is the slope of the secant line becomes the tangent line, and the slope of the secant line becomes the slope of the tangent line. Now, motivating that, we have this definition. I'm going to read this definition, and then I'm going to pause for a count of 10 Mississippi to see, how we're doing. So here is the definition of the tangent line with slope m. So if f is defined on an open interval containing c, and we're going to take this limit. Now this limit is the limit of the slopes of the secant lines. So this is the limit as delta x goes to 0 of delta y, change in y, over the change in x. And these are the slopes of the secant lines. So this is still the limit as delta x goes to 0 of, this is f of c plus delta x minus f of c all over delta x. Now you all know that limits don't always exist, and you have to calculate limits and so on and so forth. But if this limit exists, and if this limit exists as a real number right now, and we'll call it m. And by the way, people, this goes all the way back to Fermat, that we started calling the slope m because he actually said in some of his writings that the slope is like you're going up or down a mountain. And so they start saying, oh, we'll call it M, like mountain. So anyway, there's the M. So if this limit exists, it's a limit as delta x goes to 0 of f of c plus x plus delta x minus f of c all over delta x. If this limit exists, then the line passing through c, f of c, with slope m is the tangent line to the graph at the point c, f of c. Now I am going to say something, and back in high school, I think, well, if you had studied with me in high school anyway, I would have forced you to memorize the quadratic formula that, you know, the solution to a quadratic equation, capital A x squared plus capital B x plus C is equal to 0 is minus B plus or minus square root of B squared minus 4AC all over 2A. Now, the reason I'm bringing that up is in the same way that an algebra student and a calculus student wants to have that tool in their pocket to use all the time, a calculus student wants to know this definition. So I do want you to know, and we're going to call this the derivative very soon, but you want to know that the slope of the tangent line to a curve at a point C, f of c is the limit as delta x goes to 0 of f of c plus delta x minus f of c all over delta x, and that this is m. Okay, so I'm going to pause for a count of 10 Mississippi, and it's 10 Mississippi because this is an important thing. Some students might want to be writing it down, and I am asking for questions, and someone started asking a question, which is good. Please
Yes.
continue, whoever that was.
Yes. First of all, is this in the Thomas's calculus book?
Yes, it is.
Okay. Well, I'm trying to find it. So, it says page 101, right?
All right. I'll tell you what I'm going to do. I am going to stay on this collaborate call at the end, and I'm going to go to my math lab, and I'm going to log into my math lab, and I'm going to show you the page that this is on in the Thomas book. And anybody who wants to stay for that answer, you know, we'll do that. But I'm going to do that, you know, and I guess I will leave the recording on as I do that. So anybody that wants to look at it and do it. So I'm not saying I'm not going to answer your question, but I'm just going to say that I'm going to do that at the end of this period instead of right now.
Okay. I just want to make sure I write um some of this information we discussed down. You kind of went a little fast, which is understandable. I just want to make sure I can
Yes,
actually
and
just.
I am going to tie this to the Thomas textbook, but I have to log out of here to go, you know, I have to go to a different thing,
I
and
understand.
I'll do that at the end, but I will do it.
Okay.
Okay, so that is all good. And again, what I said is this, are there any other questions? Now, it's not probably the most important thing in the whole course, but I got to tell you, this is probably the most important thing we've done so far in this course. Okay, I'm going to go down then, and we're actually going to do a calculation here. And I guess I'm going to do this calculation right here. And I'm not sure how this works. I'm going to see if I can make this bigger. Yeah, that's making it bigger. Good. That's probably good. Okay. All right. So we're going to go through one of these calculations right here. And I'm hoping that you can see my cursor, and maybe you can. I hope you can. Okay. So we're going to do, this is example 1. And we're going to say, well, suppose that we're talking about y is equal to 2x minus 3. And we're going to say, what happens when c is 2? Now, this is really kind of in a sense, a trivial example, but it helps us get started. Okay, so what is the slope of the graph of y equal f of x equal 2x minus 3 when c is equal to 2? Well, let's use this definition that we just came up with. So it's going to be the limit as delta x goes to 0 of f of 2 plus delta x minus f of 2 over delta x. Now, we've got to evaluate this limit. And so what we're doing here, we have f of 2 plus delta x. Now what that means is I'm plugging in 2 plus delta x for x. So I'm sticking 2 plus delta x in here because I had f of 2 plus delta x. So when I do that, what does it do? If I give as an input, if I give x, what happens is f of x, the function machine, multiplies that by 2 and subtracts 3. So if I give it as an input 2 plus delta x, it multiplies 2 plus delta x times 2 and subtracts 3. Now what I've done so far is just calculated what is f of 2 plus delta x. Now this minus sign that I'm trying to point out here is the same as this minus sign over here. But then it says what is f of 2? Well, if you plug in 2, f of 2 is going to be 2 times 2 minus 3. So I put this here. And I'm dividing by delta x. Now I have to do the algebra. So I do the calculation, I distribute, I get 2 times this business is 4 plus 2 plus delta x is going to be 4 plus 2 delta x. I'm taking, and then I'm subtracting 3, and then I'm minus the whole of this. So that is minus times 4, and then there's a minus minus times 3. So I get this. Now notice, everybody, that the 4 cancels out with a minus 4, and the minus 3 cancels with a plus 3. So I'm just left with 2 delta x up there in the numerator. And I'm left with 2 delta x in the denominator. And I haven't taken the limit yet, so it is still the limit as delta x goes to 0. So I'm going to whack the delta x's one with another, and y'all know that limit's going to be 2. And why? This is a little bit satisfying because, gosh, back in high school algebra, you learned if I had y equal 2x minus 3, the slope of this was 2. So I guess I would say it sort of had to be 2. So that's what we have. But now we're going to do something that is a non-linear function. And we're going to do this example in the last 5 minutes that I have you. Actually, I'm going to spend more than 5 minutes, but before I, declare the class over and go and point you to places in the Thomas book. Okay, so this is, now we're going to talk about a more complicated function, and this is not a line. This is a non-linear function, and the thing we're looking at is f of x equal x squared plus 1. And we're going to try to find the tangent line at this point, and that's the blue line that we have. And you can see that should have a negative slope. And in fact, let's just focus on that one because I am very aware of how limited our time are. So I'm just going to talk about finding this tangent line here. So the point of interest is minus 1, 2, but we want to find the slope of the tangent line to the curve at that point. Okay. We know how to do that though, because we have the definition. So here we're doing the same thing. And you see, the way I'm going to ask this question later in our course is I'm going to say, use the definition of the derivative to find the slope of the tangent line at a point. And that will be, I guarantee you, that will be a problem on the midterm, probably a problem on the final too. And I'll give you some F. But anyway, that's why you want to memorize this, because I'm not telling you that again. That's what you're memorizing. You probably haven't memorized it today, but that's kind of okay. So here we go. And what we're going to do here is we're going to do this for a general point C, but then we're going to say, oh, but C equals minus 1. So anyway, this is the limit as delta x goes to 0 of f of C plus delta x minus f of C all over delta x. And then we start plugging it in. But everybody realize that the f of x that we're plugging in is this guy up here. it is x squared plus 1. Okay, so this is f of c plus delta x. So I plug as input c plus delta x into my f. So what does it do? Well, it takes whatever I gave it and squares it and adds 1. So you see f of c plus delta x is parentheses c plus delta x whole squared plus 1. This minus sign that I'm trying to point at is this minus sign, and then I say f of c. Now this is, I have to subtract off the whole of f of c. So this is minus the whole of f of c, which is going to be c squared plus 1. And then I have delta x in the denominator. Okay, now I have to do some algebra. I'm still going to be doing algebra instead of the limit here. So I'm squaring c plus delta x. Now when you square c plus delta x, you're squaring a binomial. So this is c squared plus 2c delta x plus delta x whole squared plus 1. And then I'm going to distribute this, and this is going to be minus c squared, and then it's going to be minus 1 all over delta x. Now again, and you probably see a pattern, some things are canceling. So I get c squared canceling here with this minus c squared, and I see that this 1 will cancel with the 1, and in fact everything that is left, which is 2c delta x plus delta x whole squared all over delta x, all that, there's a factor of delta x everywhere. So I'm going to factor out the delta x, and I'm not even showing you this step here, but that if you wanted to add a step, you could. I'm factoring out the delta x. And you see the delta x in the numerator and the delta x in the denominator cancel one with another. And so what you're left with is the limit as delta x goes to 0 of 2c plus delta x. Now here you can just plug it in because you've canceled out the common factor, and that means you have 2c, and the point that we were interested in was minus 1. So if we let c equal minus 1, the slope is minus 2. So you see the slope of this tangent line is minus 2. Now I'm going to count till 5, Mississippi. But you see, we did something kind of amazing there. So anyway, I'm going to pause for a count of 10, Mississippi, I guess I'm going to say. Okay, now the clock rolled over to, the end of class. Remember, we're supposed to be in a classroom on Monday. So that's the plan, and things will be better then. Now, I am not turning off the recording yet, and I'm going to be stop sharing, and anybody that wants to stay can, and one student I know did have a question on that, and maybe a whole bunch of people do. So I'm going to, I'm going to be stop sharing here, and I'm going to go back to, and you guys be careful this weekend, anybody who's leaving. But I'm going here, and I need to share an application screen. And I am going to Thomas's calculus book. But that, unfortunately, actually it's not unfortunate, it just is. That is in my math lab. And I didn't do that, but here we go. And then I have to log in. So then I'm going to that's good. And now I have to find Thomas's book. Just bear with me, we're getting there. This is probably the best place to look at it. So I'm going here. And I'm going to chapter contents. That didn't help. table of contents is what I want to look at first. Okay, and by the way, these titles are all familiar. These are, you know, things that we've been doing. We've been talking about limits. We did the epsilon delta thing. We talked about one-sided limits. We talked about continuity. There's a video that is posted that is called, you know, deals with this affinity thing and asymptotes. So we've talked about that. But we're somewhere in chapter 3, and certainly we're in chapter 3.1, which is page 102, and they define the derivative on page 106. So let's go in there then. And so this is chapter 3. And I'm looking at page 106. I'm not sure what page I'm even on here. Let me just go ahead a little bit because I do know what the question was. And I'm going to go to, all right, so as an example, here is they call it the limit of a difference quotient, but right here you can see that on number 2, this is called the slope of the tangent line to the curve at x0. And so this is a limit as h goes to 0.
Mr. Bradley?
Yes.
Well, my question was more asking was wasn't able to completely copy everything down when it came to the tangent line problem, and I was more just wanting to look at that and knowing where to find that information on Thomas's calculus so I could do it at my own, copy down information at my own pace.
Sure, and maybe I've answered that question now, have I?
Is this about when you were talking about that tangent line problem?
Yeah, where you should be reading and looking, and I'm going to go over here and expand this just a little bit. Yeah, okay, so what you should be reading to read all about this is you should be reading this section 3.1.
Yeah, I think I already well, sort of found it, but I'm still kind of confused because I don't feel like I don't know if I'm looking at exactly the same information that you were showing in the other textbook.
Well, I guess what I want to tell you is, and again, I'm not trying to be rude with this. I'm just, you know, I've been down this path
You know what?
before, and the answer is you are looking at the same.
Okay. And anyways, even if I have trouble understanding it, I could probably watch this recording later.
Yes, and you're welcome at any time in my office hour. And I mean, you can come not to my office hours. That's fine too. You're always welcome. And you know, Linda Shaw, you know, the guided study groups that I sponsor with Linda Shaw and things. So there's a lot of things that you can do. So you are, I'm going to say, almost never without math support. Okay.
Okay.
So and I think, and again, just because I've been down this path before, I think you will find peace studying both the video and this chapter 3.1 or session 3.1.
Yep. Yeah,
okay?
I'm sorry that I bothered you and kind of delayed things a little.
And please understand, you didn't bother me, okay? And in fact, I kept the recording going, so this little discussion about where it's in the book is there for some student that maybe had to leave and go to another class. Okay, so we're good now. So I think I'm going to stop sharing here. I'm going to go back to whatever this is called. Yeah, bye-bye. And I'm going to stop recording.